September 7, 2021. Okay, that's Physics 37 class. And let me just review quickly what we did before. Now it's recording, right? Now it's recording. Hopefully, I like the software because it ends up pretty good, okay? The framework of physics, what I also like to call the building blocks of physics. So just remember that. That's easy to remember, right? The basic three important building blocks. We're just reviewing what we did so far. Basic quantities, the primary definitions, and the laws of nature. Okay, here's the table completed, right? But all you have to know right now is the length, mass, and time, position, and force, and we didn't cover any of the laws of physics yet. Okay, I missed the laws of relativity here. I didn't put the laws of relativity here. There are two laws of relativity that I didn't put. I'm going to correct that. Okay, but that's for physics 39. Okay, in physics 37, we're going to see those laws right in here. The three laws of motion, the law of universal gravitation, and at least one of the laws of thermodynamics. We usually don't have time to cover all the four laws, but at least one of the laws of thermodynamics we're going to cover. Okay, so here you go. Basic quantities, length, mass, and time. Primary definitions, position, and force. Okay. So here you go. I cover that in physics 37, right? Electric charge, which is also a basic quantity, we cover in physics 38. Luminous intensity, we don't cover at all. For some reason, some strange reason, we don't cover luminous intensity in physics. We just cover optics, okay? But we do cover quantity of a substance in thermodynamics and chemistry. Thermodynamics would be P37. Okay. Primary definitions, right? And from those primary definitions and the basic quantities, we start to define other important definitions, come up with other important definitions. Okay, so here go units of measurement and standards. You can skip that. Measurement and significant figures, uncertainty, precision, and accuracy. I covered that in the lab. Significant digits, right? Here how you measure something with a ruler. Today we are going to do a lab on measurement. And there's a bunch of examples here. Here's the definition of a standard deviation from the mean. Standard deviation from the mean. Let's skip that. And that's what we were covering last time. One-dimensional motion. Position, displacement, average speed, and average velocity. There was something missing there in my notes, okay? I did cover position, I did cover displacement. And there is something else called distance that I didn't cover.
Is this document on your Google Drive?
Yes, a better version of this one is on Amazon.com. Okay, that's for purchase, a better version. But a rough version, the one that I do in the classroom, is in the Google Drive, okay? Okay, what you see right in here is the one that is my Amazon.com website. A rough version is the one that I upload to the Google Drive. Okay, so here you go. Average velocity, right? Displacement. And what I didn't cover was the motion diagrams. We can even do motion diagrams here. Okay, I'm gonna do a motion diagram with Excel. A motion diagram is nothing more, nothing less than a bunch of pictures in a single frame, displaying, documenting the position of an object, okay? So think about that. We have this particle moving along this axis here. Okay, it's moving with constant velocity, and we have this device that's capable of recording the position of the particle as time goes by. Okay, so a given instant of time is the position, particle is a position 0, another instant of time is a position 1 meter, 2 meters, 3 meters, 4 meters, and so on. Okay, so that's what we call a motion diagram. Okay, I used to do those pictures when I was a little kid. Okay, today we cannot do that. Maybe we can do that with electronic cameras, but at that time we had to do that with the mechanical cameras. We had to make several pictures in a single frame, in a single device, and I was able to do that at that time. So when we can come up with those motion diagrams using Excel. Okay, we can even do movies with Excel. Let's do that together. Here you go. I'm gonna get Excel right in here. Excel is a very important tool, very useful tool, by the way. I'm gonna create, if you have access to Excel, it's gonna help you a lot understanding physics. You can create simulations, you can create movies with Excel. Okay, provided you know how to program it. And let's see, freeze panes. Okay, that's a very nice feature of Excel that I like. I learned about this feature here of Excel freezing frames from my girlfriend. You know, see, I learned that from her. And see what happens if I don't have freeze frames here. You know, look what happens to 1, 2, 3, 4, 5. They become hidden, right? If I go to the right, the A column also becomes hidden. But sometimes it's very useful to keep the this cell here and this column here and this row visible. Sometimes it's very useful to do that. How do you do that? You select the cell, go to freeze pane, and you freeze the pane. And now the row 1 and the column A is frozen there in place. Sometimes it's very useful to do that. I like to use freeze frame. Okay, and what we're going to do, we're going to do a motion diagram. I'm going to put it here, motion diagram. Rename. Okay. And how we are going to do that. Okay, I'm going to get it here, X and T, and X and Y. And I'm going to get also T right in here. Okay, T is going to be in seconds. X is going to be in meters. And Y is going to be in meters as well. Okay, at this point in time, you know, we're going to start at T equal to 1 second, 2 seconds, 3 seconds, and so on, right? Here you go. I highlight this guy here. Let's go all the way up to 10 seconds. Here you go, 10, no, 9, one more. Okay, 10 seconds. Now, let's say, is the position of a jogger. Okay, someone who's jogging along a straight line. He's not moving in the two-dimensional plane. He's just moving in a straight line. And joggers usually, you know, they jog roughly at 2 meters per second. Roughly, their speed is roughly at 2 meters per second. Okay, and I'm going to write down the equation of motion for my jogger. He's going to start at the origin. Okay, it's 2 meters per second times t. Okay, so he starts at the origin of the coordinate system. As he keep on jogging, he's at position 2, 4, 6, and so on meters, right? And because he's undergoing one-dimensional motion, the y coordinate is going to be 0 all the time. It's going to be constant. Make sense? Right? And now I can plot. So here you go. Take a look at the equation. Here's the equation. 2t, 2 meters per second times t. That's the equation of motion of this jogger. I didn't display the a here is my t, right? The a here is my t. I didn't display the unit here because Excel doesn't recognize units in the cell that is making the calculations. Okay? Everybody's familiar with Excel here? Do you know how to use that? Okay, good. So now we're going to plot my motion diagram. I'm going to highlight X and Y. Okay, insert, scatter. So here you go. Let me see if I can get it. See, the screen is very small. Unfortunately, maybe I will figure out a way to hook up this computer to the big one here, and we're gonna have a larger screen. Okay, here you go. Here's the motion diagram of the jogger. Right? 0, 2, 4, 6, blah blah blah, constant velocity. That's, that's trivial, right? Constant velocity is trivial, right? What might not be trivial is accelerated motion. Accelerated motion, uniform accelerated motion. So this is constant velocity, and let's see how uniform accelerated motion is. All right, I'm going to. Any questions about that? So go uniform. Okay. And now I'm going to. Let me see how I'm going to do it. I'm going to put X sub U. X sub U for uniform motion. I want to distinguish this one from the next one that we are going to work with. Subscript. Okay. And now we're going to do accelerated motion here. The equation of motion is going to be different. The equation of motion is going to be different. So let's say it's 1 meter per second square. And you start with at the origin. You start at rest. Okay, 1 meter per second square. How do we write the equation of motion for 1 meter per second? Is half, right? The acceleration, here you go, the acceleration is going to be 1 times t squared. Remember that last class? Right? I'm going to write down the board. That's not going to show up in my video here that I'm doing. So here you go. The first one, uniform motion. Uniform motion was x equal to vt, right? V was 2 meters per second times t. That was the first equation was that I put there in Excel. For constant acceleration, the position is going to be half at squared. The initial velocity is 0, the initial position is 0 as well. And that's what I have here. I am using an acceleration that is 1 meter per second squared times t squared. Right? You do dimensional analysis, and you get the right unit for the x. That's the one I have right in here. So let's go ahead and plot and click and drag one-dimensional motion, and let's see what happens. Okay. Initially, initially the position of the particle is less than the other one, right? That's because the initial velocity here was not zero, but the initial velocity here was zero initially. But as the particle accelerates, it starts to catch up with the other particle that's moving with constant velocity. See that? See what's going on here? Eventually, it overtakes it. Overtakes the other one that's going on that's moving at uniform velocity. Eventually. And I'm going to do the following. I'm going to try to plot in the same graph. Let's see if I can do that. No, that's okay. I'm not going to complicate. I'm going to plot in a different graph. Here you go. Insert. Okay, so here you go. Now here, that's how a motion diagram looks like for a particle that is uniformly accelerated. I'm going to try to put both graphs in the same scale for comparison purposes, okay? Here you go. This guy goes all the way up to 60, so I gotta put this one all the way up to 60 as well. Here you go. Okay? So that's how it looks like. Initially, the particle moving at constant velocity is ahead of the other. Is ahead of the one that's being accelerated. Okay? That's the first point. That's the first point. First point for accelerated particle, first point for uniform motion. That's the second point for uniform motion. That's the second point for accelerated motion, and so on. Third point, see? Eventually, the particle that is accelerated catches up with the other one. Oh, let's see. I gotta do better. Yep, gotta watch out what I'm doing here. You know what? I can. Yeah, it's not in scale, right? Let's put that in scale. Here you go. Now we have it right. Right? Did you notice that? Just not in scale initially. Okay? 2, 4, 6, 8. Yeah? Okay, that's when the accelerated particle catches up with the other one that's uniform, is moving uniformly. And then it just, moves away. Further and further away. Okay? That's what motion diagram is all about. We can do motion, again, like I said, we can do motion diagrams in Excel. And that's the way you do it. Motion diagrams in Excel. Okay. Let's go to the next one. That's what this chapter is all about. Here you go. You saw that before, right? Position, displacement, average velocity, instantaneous velocity. You saw that. You saw that in the previous section. We're just doing a quick summary on that. Okay. Here is another example of different type of motion. Okay. So far, the type of motion that you have to work is constant uniform motion. Uniform motion. Constant velocity. And the other one is uniform acceleration, which is constant acceleration. But there is another type of important motion that is, we are going to see that in physics 39, okay, is simple harmonic motion. In simple harmonic motion, the particle moves just like that. The motion of the particle is in terms of a trigonometric function, either a sine or cosine. Okay? And that's what this example is all about. This example is all about. You want to know the velocity of this particle. What do? You take the derivative with respect to time. Right? You want to know the acceleration of this particle. You take the second derivative of x with respect to time. Here, I did all this step by step, and okay. What else you have to know? Acceleration. Remember the algebraic method that I told you? Is all derived here. Is also that in that note that I uploaded for you. Constant velocity and constant acceleration. How to get the equations of motion for constant velocity and constant acceleration. Okay. And what I didn't show to you is the graphs. I didn't discuss that with you. I didn't discuss how you plot the graph for constant velocity and constant acceleration, okay? But I did mention to you that there are, a few graphs. Let's start here. New. I'll be switching back and forth. I like to do things in real time, otherwise it becomes too boring for me just talking about something that's already in there, right? So here you go. Graphs that describe the motion of a particle. Okay, so here you go. Okay. Okay, so here you go. Let's start with uniform motion, which is constant velocity. Okay, for this type of graph, you already know that the acceleration. I'm going to put here the equations of motion. Equations. The acceleration for uniform motion, you should already know that acceleration is 0, right? Make sense? So the equations of motion for uniform motion is acceleration 0, velocity equal to constant, and position is going to be, the initial position, x naught plus vt. I'm going to put x naught right in here. Okay. That's for uniform motion. And then we have accelerated motion. Let's put that uniform acceleration. Constant acceleration. Acceleration. The acceleration is constant. The velocity becomes v naught plus at. And the position becomes x naught plus v naught t plus half at squared. Here you go. Now, how do we plot those graphs? How do we plot those graphs? I already have the data for me to plot the graph. Have you remember that? I already have the data to plot. So we have the following graphs. We may have the following graphs. We may have the following graphs. We may have. A versus T. Okay. V versus T. And what else? X versus T. Right? We can have all those graphs. Okay. Let's start with this one here. Okay, for this case, I'm gonna put it right in here. Here you go. X versus T. Don't forget to put the units, right? Every time that you do a graph, you come up with a unit. Okay, the most, you can have something like that. That would be what? That would be uniform motion. Uniform motion because the derivative here is constant. The derivative is constant right in here. Okay. In this case, the velocity is greater than zero. The initial position is greater than zero. Okay? Greater than zero because the slope is positive. Right? You can have another case in which the graph is like that. Okay? In this case, v is still greater than zero, and x naught is less than zero. Okay? And then you have what? Something like that as well. Still uniform motion. In this case, v less than zero and x naught greater than zero. Okay, we're doing that a generic treatment. You can put whatever number you have in there. That's the type of graph that I'm going to see out there. And then you have another one. Okay, we can have something like that as well. Here you go. V less than zero, x naught less than zero. Those are all the possibilities that we can have, right? For the position in the case of uniform motion. Now, what about accelerated motion? Okay, for uniform motion, the velocity and the acceleration is trivial, right? Velocity versus t can be like that, but can be like that as well, right? Acceleration for uniform motion will always be zero. Okay, here we go. S meters per second, A meters per second squared t. Okay, the acceleration will always be zero, so it will coincide with the x-axis, with the horizontal axis, which is the axis for t. Now, what about for constant accelerated motion? Okay, we can start. I like to start with the acceleration, right? Acceleration graph. Acceleration graph can be either positive or can be negative. Okay, in this case, the velocity will vary uniformly. I'm going to put you here. this one is not being recorded there, right? I'm recording only my screen. So we can have two possible velocities here. You know, either one like that, in which v naught greater than 0, or another one like that, in which v naught is less than 0. Therefore v naught is and then that gives rise to two other possible graphs, right? For x. Are you following? So here you go. X and t, v naught positive. So what does it mean v naught positive? It means that the slope right in here of my graph is going to be positive, right? The slope at this point at t equal to 0 is going to be positive. But you also know it's going to be a parabola. Okay? The parabola is a positive parabola. So it's a parabola with the concavity upwards. Make sense? So here you go. It's going to be something like that. Okay? Something like that. I don't like it. I put my slope like that. So let's see. Let's do like that. My parabola like that. Right? For this one. Right? And that x naught greater than 0. But you can also have x naught less than 0. You can have, let's say, a time t equal to 0, right? V is going to be, V naught is going to be positive. So again, we are going to have a positive slope there, that spot. The concavity is going to be upward, so, you know, it's going to be something like that. A parabola, you know, it's difficult, a little bit difficult to draw it, but you got the idea, right? And then what about the other ones? And then you gotta do the same for this one here. And you gotta do the same for this one as well. Okay? I did only what? I did only for this one here. And you can do, you know, for this one as well. With a negative velocity, negative initial velocity, in which the slope is going to be on the other direction. Okay? Times that. 558. Okay, we need to have our break, right? So let me save this guy here. P37 notes. Okay, this one is 090721. Okay, so it's 6 o'clock right now. Okay, let's be back at 6:15. Okay. Do you need any help?
They need to sign.
Okay. What about her? Do I need to do that for her too?
Did you pick up the graphical? Yeah.
Okay.
Oh yeah.
Do I have to sign yours too?
Yeah, so what you're gonna have to do is give us the actual code for the lecture.
Yeah, let's give it.
No. No, no, no. Thank you so much. No, you didn't give us the code, the actual code.
I have permission code. I never.
They gave me the slip, but that's all I know. Oh yeah, yeah, you're right. Sorry, it's because I did it with my other professor.
Yeah.
Yes, so we have to do that.
So you have to do yours separate.
Yes.
Did you pick up one?
No, I haven't.
Okay.
So yeah, you have to sign it, and then we just add it with the permission.
Yeah, we have to go get one.
Okay, can you fill that out for me? You know, because you're transferring from the section on Tuesday, right?
Do you have both section numbers?
Yeah, it's in the internet here. Let's see.
Professor,
Yeah.
I have a question about the partial exam. Are you gonna let the lecture out early on that day? Because you said it's from 7 to 9.
9, yeah.
But lecture ends at 6:50
The lecture,
on Tuesday or Thursday.
yeah. Let's see, you're asking the exam, right?
Yeah.
Okay. Yeah, I'm still deciding. Okay, it looks like we're gonna do the exam on Thursday from 7 to 9.
So
Okay.
on that day, is the lecture gonna be shorter?
No, no. On that day there will be no lab. Okay.
Okay.
On that day there will be no lab.
But the lecture ends at 6:50.
So are
So
you
how? You
Yeah.
said the exams are on Canvas, right? That was my
Yeah,
question
yeah,
as
yeah,
well.
yeah. That's right. Let's see. How, yeah, you have a good point here.
you need time to get home?
Yeah, you're right. You need time to get home. Yeah, you're right. Half an hour is good enough.
Yeah.
Half an hour is good
But
enough.
for us, I don't know for the rest.
Yeah.
Like we can
Yeah,
get it.
we'll sort that out until then. Yeah. Yeah, yeah, and I have to get home too. It's not just you. Yeah. We'll sort that out. Maybe we do from 7:30 to 9:30.
So is it gonna be live, like on Zoom, or just?
Yeah. Yeah, and so, or maybe, I'll figure out how to do that. When we were having the coronavirus crisis, I was doing, on Zoom, but I was right there at home, I didn't have to dislocate from here to there, right? So let's see, schedule and catalogs. Uh, um, leave that alone. Okay, so here you go. Lab. See that? That's the Tuesday
You want me to
lab.
come on that side?
Huh? And that's the Thursday lab. Okay. You're moving from Tuesday to Thursday, right?
Yes.
Okay. So the Tuesday lab, did you write that down already? 12 2 2 2
Okay.
to
And the Thursday.
25 290.
What do I have to
Transfer
write it here?
from, yeah, transfer to
Oh.
25 290. Okay.
And course name and number.
Physics 37. Then you put lab. The units, I do not know what you do there because the labs, I believe, doesn't have any units.
Okay.
Ask the woman there.
Yeah, that's
And,
fine.
and you want me to sign, right? Oh, you gotta sign too. Yeah. Sign it yourself first. You already put your name there. Let me see. And then the other girl gotta do something about
Yeah. She's gonna bring something like this under her
yeah.
name. So my question is about the Kindle version of your PDF.
Uh-huh.
Do you know if we have to subscribe to Kindle to get those, or do we have to?
Let's see. There are two ways, right? If you are a Prime member,
Mhm.
you can get anything that's there, any ebook there for free. Of course, you're paying the Amazon $15 a month, right? I don't think you want to do that. Or, okay, you buy
Kindle
the
version.
the ebook,
Mhm.
download the Kindle app.
Okay.
First, the Kindle app is free,
Mhm.
so you can read the ebook.
Okay, but so when it gets updated, we just.
When you get updated, you just call them. You just call them and they'll tell you how to download
So if we have
the
Prime
PDF.
already, then we can just get that book and.
Yeah, for free. Yeah, you're
And
paying. I don't know what you're paying. $15 a month, right?
yeah, we have a family Prime, so we
Ah,
can.
you have a
Yeah.
Prime Prime. Okay.
And for like we can download more than one book because we are both in the same
Yeah,
household.
yeah,
Because I wanted to download the lab manual.
yeah, yeah. If you have Prime, you have access to the whole.
Yeah, but we can have more than one from
Yeah, yeah.
Amazon.
I'm quite sure you can. Yeah.
Okay.
Ask Amazon. I don't have Prime myself, but once you buy their service, $10 a month or $15 a month, some time ago I had it. Okay, I understand you can download any ebook that is in the Amazon store.
Oh, nice.
Any. I think it's any ebook that's in the
Okay.
Amazon store. Yeah.
Okay.
But you have Prime, right?
Yeah, yeah.
Have you ever downloaded any books from it?
No,
You haven't?
I didn't.
I have Prime Video. I don't have Prime, the regular Prime. I do not know if it's the same thing.
I think it is.
It's the same thing?
Because when you have Prime, you have access to Prime Video.
Yeah?
That's what I know.
Oh, yeah, they come up with all those servers. We get lost.
Okay, thank
So I
you.
got a question about the exams day. So on the exams day, we're gonna do the exams on the campus,
Campus,
right?
yeah.
So we have to go home and do it, something like
Yeah.
that.
Or you can do here on the campus, right? If you have your.
Yeah, because I live in Cypress in Orange County.
Was it?
I live in Cypress in
Cyprus?
Orange County,
Yeah, how long does
so
it take to get there?
it's like 30 miles.
30 miles, right? How long does it take to get there? Half an hour more, right? Cyprus
Yeah,
is
like
far away.
45 minutes maybe.
45 minutes.
So when the class finish at 7,
Uh,
it would take me like for like I'll be at home by like 8.
yeah.
So when I get home, maybe like 5 minutes till we can start.
Yeah, that's right. Yeah, I gotta take that into account. Let me see what we're going to do. Maybe we have to stick with the exam during the lecture time. Yeah,
Yeah, okay.
maybe we have to do that. Lecture time, there's no problem.
Or like maybe like on weekends.
Weekend?
Yeah, like weekends morning.
But not everybody will be able to do it.
Yeah,
That's the
if
problem.
you ask other people, maybe they'll be normal.
Yeah, I don't know, there's a question of, there's a name for that. Is
Yeah, I just wanted to
yeah.
make sure that you know.
Yeah. You have a good point. Yeah, if you have to drive all the way down there, it's going to be, and then what if you get too much traffic and it takes 1 hour and a half to get there, right?
Yeah, sometimes it's
That's yeah, it doesn't look like it's gonna work doing that on the lap time.
thank you for that.
Uh,
Yeah.
Now it's okay. So I'm just gonna repeat what I said before, right? Okay, here you go. In a graph x versus t, in a graph x versus t, the slope at any instant of time, any instant of time coincides with the instantaneous velocity at that moment. Okay? Okay. Also, so we can do the same for the acceleration, right? Recall also that A is dv dt, right? In a graph v versus t, the slope at any instant of time is the, not coincide, but is the instantaneous acceleration at that moment, okay? Not coincide, but is the, right? Make sense? Okay? So now let's go to the next step. Okay. Also, here you go. I'm gonna put here also. We also have, you know, we also have, here you go, multiply both sides by dt, right? We can multiply both sides by dt, just like I did before, last time. When I do something like that, what do we get? I get dx only, dx equal to v dt, right? And then, just like I did before, when I apply the integral on both sides, go. I'm going to apply the integral here. It doesn't matter if the velocity is constant or not. What I'm doing here applies to any type of motion. Okay? And let's see, I can get it. I'm going to copy this one here. When we apply the limits, we get x naught to x, and then v naught to v. To v. Right? So what we end up getting here is delta x. Delta, oh, it's not v naught, sorry. It's t naught. And we usually put, remember, we're integrating on t, right? We usually make the t naught equal to 0. From 0 to t. We're integrating on t, not on v. So the limit must be on t. Okay, apply to t. What this equation means, okay? So let's say my v is a function of time. Let's see here. Oh gosh. Brackets. That's the problem of using a small screen, those things are all hidden. Here you go. The v can be a function of t, okay? So what this equation means here graphically, in a graphical sense? It means that the area below the curve is delta x, okay? That's what it means, okay? Let's see what's going on here. Huh. How do I get out of it? Okay. Oh boy. No. Good. Okay, so what does the above mean? Well, it means that the area below AV versus T graph is the displacement. Okay, is the displacement. Okay, we can do the same for the acceleration. Okay, so here you go. Let me put one more. I'm gonna put one more equation right in here so it looks better. I want to start with this. Oh, okay, good. So I'm going to repeating for the acceleration. Okay, here you go. We also have acceleration is equal to dv dt, right? Multiply dt on both sides, and we end up with what? Dv equal to a dt. Okay, we change the integrand to dv. So, oh, that's not what I want. But now the limit is v naught to v. And here, well, we can say that acceleration can be in general a function of time as well. It's not a function of the time all the time, but you know. And then the area, what we get? We get that the area below the graph of the acceleration versus t is going to be a change in velocity. Okay? That was something that I didn't cover last time. Graphical interpretation for those results that we have. So here you go. What does the above? I'm just gonna copy and paste here and change, make some minor changes. What does the above means? It means that the area below a an a versus t graph is the change in velocity, delta v. Okay, so save it. Going back to my PowerPoint, let's see here. Let me see if I have an illustration of that. Yeah, it doesn't look like. Oh yeah, I have here. So set up slideshow. Present a full screen. So here's time, hide slide. Yeah, okay, so here you go. A against T. The area below is delta V. Is that large enough for you folks there in the back? Yeah. Let me group. Here you go. In case it's not. Yeah, okay, like that. Save it. So here you go. Here's some. Okay. Constant acceleration, right? I covered that. Here you go. What this graph means here. This graph means that acceleration is what? Positive or negative? Positive, right? What about the initial position? Positive or negative? And what about the initial velocity? Negative, right? Initial velocity is the slope right here, this spot. Okay? That's how you read those graphs. Let's see, we have more. Here you go. Okay, the corresponding graph for the velocity of, is this one right here. The initial velocity is negative. What about here? Let's see. Yeah, it's still negative. And what does it mean here? What's the value of the slope at this instant of time? 0, right? So it is what? It is at this instant of time right in here, right? The velocity was negative, and it's becoming less negative, becomes 0, and then start moving in a positive direction. Okay? The case of this pen, think about this pen, okay? I'm gonna make a quick demonstration. I'm gonna propel this pen upwards. While the pen is rising, the velocity is positive, right? But then it is a positive value that's decreasing, by the way. However, when it reaches the peak of the trajectory, the instantaneous velocity is what? 0. And then what happens to the velocity? It becomes what? Negative. Can you picture that? And then when I do my axis, positive direction in the upwards direction. Okay? So those are exercises that you can do. At this instant of time, what do we have? You have minus V naught divided by A. You can calculate that. It's possible to calculate that. Okay, all you have to do is to get dx dt equal to 0 in your equation of motion. You want to do that? Let's do that together. Okay, so here you go. I'm going to get my notes right in here. Find, so the exercise is the following. Find the instant of time t. Let's see. Let the equation of motion of a particle be, x equal to x naught plus, oh gosh, what happened here? Plus v naught t plus, I'm gonna fix my first v naught. Okay, hang in there. He's gonna be x naught. X naught. Where? Oops. Where v naught is less than 0. Okay. The sign is implicit right in here. Less than 0 and a is greater than 0. Okay. Find the instant of time at which the the velocity of the particle is 0. That's a nice exercise. Nice example. Okay, solution. Think how you do that. I'll give you, 2 minutes to think about that. Try to solve that yourself. You know V naught, you know A, you know X naught. Okay, I'm not putting numeric values in there, but that's the most powerful way of solving an equation, solving a problem. Someone left that here. Trash it. Solution. You figure out already? You want the dx dt equal to 0, right? And find t for dx dt equal to 0. Okay, so dx dt equal to 0. So dx dt becomes what? Equal at. Let's not forget we want to solve it instead of time for which the velocity is instantaneously 0. And then we have to solve this equation right in here. This one goes to the other side. Multiply and divide both sides by a, right? We get v naught divided by a. Because your v naught is negative, your t is going to be positive, and the problem has a solution. But if v naught were positive, this problem would have a solution only if the acceleration were what? Were what? Negative, right? But if both v naught and a are positive, there is no solution for this problem because the time cannot be negative, right? And you can see that from the graph. Save it. 639. Let's move forward. And not this one right in here. Okay. Constant velocity, constant velocity. Okay, we did that. We did that in the classroom last time. Can you skip that? Interception problem. You can look at the interception problem if you're interested, okay? That's an interception problem that you folks may be familiar with. Is the case of the surface-to-air missile, the Patriot surface-to-air missile, right? The missile, anti-missile. Right? During the Gulf War, we are using those missiles there in the theater of operations. Okay, anybody is the military here? No? Nobody's. I had students that went to Iraq during the war, you know? They're telling me their war stories at that time. There was this guy that was in Fallujah, and he got hurt, and then now he was at that time, not now, at that time he was taking physics courses. You know, he left the military and he was taking physics courses. So I like to tell those stories, right? So the Patriot missile is a case of an interception problem, okay? But it's a very complicated one. You have to shoot down a missile that is in flight using another missile, okay? But then you can use your physics to do that. But like I said, it's a difficult problem to solve because it involves propulsion, it involves air drag, it involves another particle that's flying the space in the three-dimensional, is a three-dimensional motion, and so on, okay? So we don't do this type of problem here in physics. What we do something simpler, like, for instance, a cop trying to intercept someone that's speeding by him, okay? That's one type of problem that we do. Okay, it's possible to solve. Here you go. A speeding car moving with constant velocity passes by a police officer who is initially at rest. Okay, remember that Excel spreadsheet that I did right in here? Right in here? Remember that? It's exactly what I have. Is exactly a case of an interception problem, right? Here is the speeding car. Here is the police officer. The police officer is initially behind the speeding car, but then eventually he catches up with the speeding car. In this case here, it takes 8 seconds for him to catch up with the speeding car, right? It takes 8 seconds. So that's one of the simplest type of interception problem that you're going to see out there. If you want to learn how to shoot down a missile in flight, if you want to learn how to couple your spaceship to the space station, those are all interception problems, okay? Before you go for this type of problem, which are very difficult, first you have to learn how to solve this type of problem here. That's much easier, okay? And what that problem is all about. Let's see here. Here you go. If the officer starts moving his acceleration at the present speed, the moment the speeding car passes by him, how long will it take for the officer to catch up with the speeding car? Okay, at which position will the officer intercept the speeding car? What velocity will the officer be moving once he catches up? Okay. So I'll leave that for you to think. The solution is here. Okay. Notice that nothing has been mentioned about how the police officer is going to stop the speeding car, right? We're just talking about an interception problem here. Now, how we are going to catch the speeding car, make him stop, and so on, that's another story, okay? That's another story. So think about that, how you're going to solve this problem. The solution is here, okay? The solution is right in here. I believe I plotted, oh yeah, I plot the graph right in here. That's when graphs come very handy. That's when graphs comes very handy, okay? So here you go. Here we have the speeding car, the equation of motion for the speeding car. Position times versus t. Right? It's this guy is moving with uniform motion, uniform velocity. Position is linear with time, and now we have the police officer that's going to start from rest, and he's going to accelerate until he catches up with the speeding car. Make sense? Position of that's the condition. The condition is position of the police officer must be equal to the position of the speeding car. Now take a look at the slope of the police officer, or the car of the police officer. Who is moving faster? Who is moving faster? the police officer, right? He starts at this lower speed. He's gonna catch up with the other guy only at the moment, only when if he has a higher speed, right? Okay, so that's one way for you to visualize this type of graph. And if you want to solve that, all you have to do, get the two equations of motion of the police officer and the equation of motion of the speeding car. Make the position of the police officer equal to the position of the speeding car, and you get the instant of time, and with the instant of time, you can get the position as well. Okay? That's how you do it. Let's see. Okay, so that's a variant of the previous problem. Now the police officer has an initial velocity. Okay. Now, okay. Now let's talk about, we have how many? Oh, 5 more minutes. Okay, I think that we can stop by. We can stop now. I just want to mention that the problem of free fall, okay? And free fall is defined as, the way we define free fall is what? The acceleration of the object is equal to the acceleration of gravity. Okay? Back at the time of Galileo, he discovered after a series of experiments, he didn't have the equipment that we have today, but he discovered that the acceleration of gravity was 10 meters, approximately 10 meters per second square. It was uniform nearby the surface of the Earth. Make sense? Okay? So think about that. With nearby the surface of the Earth, objects that are falling through space, they are uniformly accelerated, assuming that you can ignore air drag. Okay? So because they are uniformly accelerated, you already know what's going to be the equation of motion for something like that, right? So that's what you're going to see next time. And with this type of knowledge, you might even be able to determine the height of a building. That's a practical application of this knowledge. Okay, a practical application of this knowledge is in the determination of the height of a building. And you're going to do that. And let's see if we have something else. This one here is going to be an experiment that you're going to do. Not today, but this is going to be the second experiment. It's an example, and that's the only two things that we need to do to finish this chapter, okay? So it's 6:48 right now, so you can stop now, and we can meet upstairs for the Tuesday lab. And if you are in the Thursday lab, I'll see you on the lab next. I'll see you again on Thursday. Now let's see. I'm going to